Okay, so let's finish up chapter 7. We're looking at competing reactions with substitution reactions, so we're getting into the eliminations. There's a few extra homework problems about this, and we will see it probably again and again when we move into the alcohol chapter, among others. Okay, start off with why and when do we get elimination reactions? It pretty much comes down to the presence of a nucleophile or not. If you remember back earlier, when we talked about a nucleophile, had that abbreviated as nuke with a pair of electrons. Okay. So a nucleophile was something that could donate electrons. If we don't have a nucleophile, we need to find some other source of electrons. And that's ultimately where our elimination reaction really jumps in. So if we take a look at an overall reaction as shown below, you'll notice there are some boxes there. We'll talk about those a little bit later. We can look for the bonds broken and the bonds formed in the process of the reaction. We very clearly broke the carbon halogen bond in this case, and in most cases all we'd end up seeing is that we then formed the carbon-carbon pi bond. Okay. Since we were extra nice here, you'll notice that it's also hopefully apparent that we broke the carbon-hydrogen bond. Okay, just like we did with the substitution reaction, we did want to look at the options for a mechanism. How did this reaction actually occur? And you'll notice when we go through and look at those options down below that the formation of the carbon-carbon double bond isn't expressly stated. It's pretty much saying it's happening in each case. Okay, and where that's really coming from, or to understand where that's coming from, we really should take a closer look at the carbon-carbon double bond. Okay, so when we evaluate that carbon-carbon bond, we could say that we've got resonance structures where that pi bond of electrons, oops, I don't want to go that direction, where those pi electrons are being held on one atom versus the other. Okay, so if I decide to do that and move the electrons to one of those carbons, I would then put a lone pair on that carbon, and since it's now gained electrons, it would be negatively charged. Well, what happened to the other carbon? Well, it lost electrons, so it would be positively charged. Since the only thing I've moved here are electrons, and no atoms have changed place, no sigma structures have changed, I do have a resonance structure, so I can use my double-headed arrow. And why this is important is if we now go back to our reactant and look at the electrons in the bonds that were broken. Okay, well, the carbon-halogen bond, as hopefully you're comfortable with now, those electrons would probably go with the halogen. Okay, why? Halogen is more electronegative. Okay, so we would expect what charge on the carbon to start forming? Good call, we're looking for a positive charge. Okay, so the next part is to evaluate that carbon-hydrogen bond, and that's a little bit trickier to think about. Okay, we said that those two atoms in a bond form a covalent bond, which means complete equal sharing of electrons, which means no polarity associated with it. Okay, and we kind of stuck with that definition, and back way when we first introduced it, said there's a pseudo exception to that, and this is that pseudo exception. Which atom is more electronegative, the carbon or the hydrogen? Yeah, the carbon is slightly more electronegative, which means if I'm going to break that bond, I would expect the electrons to go with the carbon, not with the hydrogen. Well, what happens to the carbon then if we broke that bond in that fashion? Become negatively charged. Okay? If we compare our standard bond breaking and forming to our resonance structure, you'll notice they are identical. Okay? So when we're going through and trying to evaluate how our bonds break, we're going to be focused primarily on just the breaking of the bonds, not so much the formation. Okay? So just kind of be aware of that. The next part is looking at those three possible options, we get three again, just like we did with the substitution, and we want to try and determine, how it could occur. And just like with the substitution, we can either get our leaving group leaving, then breaking the carbon-hydrogen, doing it all at once, which is that second one, so we can accent that. All at once. I can spell once. You can understand what I said. Or we could try and break the carbon-hydrogen bond and then have the halogen leave. Okay, so three options. And of those three, we really don't have a clearly defined, this one doesn't work, like we did with the substitution. Remember our third option in the substitution reaction, we formed 5 bonds, and we can't possibly do that. Well, in this case, we don't really form a 5th bond. So none of these really is a giant red flag that that's just terrible, we shouldn't look at that. However, let's take a look at that carbon-hydrogen bond, breaking that first. Okay, we already talked about an issue with this. We've defined that bond as being a covalent bond, equal sharing of electrons. It really doesn't want to break. It's not going to be an easy bond to break. And so the likelihood that that happens before our halogen leaving is really, really, really unlikely. So we're pretty much eliminating that one based on just odds. It just doesn't make sense, physical sense, for that carbon-hydrogen bond to break first. Okay? Which means, just like with our substitution reactions, we're going to go down to 2 possible ways that our elimination reaction can occur. Okay? So we're going to look at our halogen leaving and then breaking the carbon-hydrogen bond. So once it's left, once our halogen bond is, our halogen has left, then it'll be a little bit easier to break that carbon-hydrogen, because then we're trying to stabilize a carbocation. So it makes it a little bit more sense. Or we could try and do it all at once. Okay, and just like with the substitution, we're going to evaluate, look at those mechanisms, and decide what things are going to control each of those individual reactions. Okay, so let's go ahead and take a look at the unimolecular reaction, or our first option. Okay, and just like what I did with the last slide, I'm going to draw it out generically and just show each of our individual atoms. You'll notice that I'm also not specifying what those carbons are bound to, other than the hydrogen and the halogen. And that's because at this stage in the game, we don't really care. Okay? First, we want to get the basics of the mechanism laid out, and then we can advance from there. Okay? So, our very first step is that we need to break the carbon-halogen bond. So what we're going to do is take the electrons in that bond and move them towards the atom that would most be attracted to them. Well, which atom would that be? That should be our halogen. Okay? Because our halogen is more electronegative. And sorry, I forgot the lone pairs. Let me go ahead and add those on there. Okay? So what's the result of that? Well, we didn't do anything to our other carbon yet, so we can do everything just like normal for it. We didn't do anything to those other bonds, and then we've got our halogen, which could be a leaving group in any other circumstance. Okay, picked up those picked up that pair of electrons. So we'll go ahead and show that in red as well, so that you know where the electrons went. Okay. What else is a result of this? Well, our halogen is now a halide because it gained electrons, so it's now negatively charged, and our carbon is going to be positively charged, or a carbocation. Okay. This first step should look really, really familiar. Okay. It should look very much the same as the SN1 first step. Okay, and that's because effectively it is the same. Okay, we've got the leaving group leaving, carbocation forming, which means if we think back to all the things that controlled our SN1 reaction, though a lot of those are going to control our E1, or our elimination of the 1 type reaction. Okay. And when we're doing the substitution reaction, the next part of our step was that our next step, rather, was that our nucleophile could attack. Okay, well, our nucleophile came in and attacked because we had the positive charge, and our nucleophile was negative. So we were trying to find electrons to stabilize the positive charge of that carbon. Okay, so we look through the rest of our solution to see what's there. All I really see is atom X. Well, if atom X goes back, I just get the reverse reaction, and that's not particularly fun, okay, or interesting for that matter. Okay, and that might have been our first conclusion, that nothing happens, but then someone went ahead and did the experiment and saw, yep, something did actually happen. So we've got to figure out what that occurrence was. Okay, so if the halogen didn't go back, I've got to find electrons somewhere else, and the only other place has to be within that molecule, okay, within my carbocation structure. So where are there electrons within that structure? Okay, good. We've got them in the bonds immediately next to that carbocation. Okay, so in the case of SN1 reactivity or cation stability, we could say that's a tertiary cation and it's stable, or it's primary and it's unstable. Okay, but do those electrons permanently stabilize the carbocation? Okay, to permanently stabilize it, I must bring electrons in that gets rid of the charge. Okay, so one option, let's go ahead and take this structure, or take just that carbon, and I'm going to rotate it on its side like we did before with the SN1 reaction. So we've got one bond coming out at you, one bond going away. Remember, it's an sp2 carbon, so we've got our p orbital. Okay, to permanently stabilize that cation, I must bring electrons into that orbital. To get electrons into the orbital, it must be overlapping, okay, either directly or through a parallel orbital. Well, if we take a look at the sigma bonds, our solid line or our wedge and our dash, those bonds, those three bonds, are in perpendicular orbitals. Okay, the plane of our, or the p orbital is coming in and out of the plane at us in our original drawing. Okay, the one I've got boxed in black here. Or it's in the plane of the paper where we've moved the molecule now, where we can show the atoms now coming out of the board at you and behind the board. Okay, so we're in a perpendicular orbital. Those electrons cannot permanently stabilize the structure. Okay, which is a bit tricky of a concept, but that's what we have to deal with. Okay, so that means we have to find an electron source somewhere else. So we could move one atom further away and jump to our carbon. Okay, well, carbon versus carbon, that's really not going to want to steal electrons from. And even if it could steal electrons, it's going to steal the electrons closest to it, which would be in that bond, not necessarily from the atom. So we'll move one section further away, and we now move into the bonds, okay, which I'll highlight in blue. Of those bonds, at this stage in the game, we only know what one of them is attached to. The other ones we don't know anything about, kind of intentionally, which means I'm going to have to somehow get electrons from that hydrogen. Well, so let's evaluate it just like we did with the carbon-carbon bond. Carbon-hydrogen, covalent bond, equal sharing of electrons. Wouldn't expect it to break, at least based on our initial definitions. If we go back and look at the difference in electronegativity, however, carbon is more electronegative. That hydrogen, or the electrons in that bond, can probably be taken away to help stabilize our positive carbocation. Okay, so what we're doing is breaking a bond that may not actually want to break to begin with. Oh, this is going to be fun to erase. But in the process of doing so, I generate a more stable product. Okay, what do I mean by more stable product? Well, in our first case, we've got carbon as a positive charge. One of our products, okay, if we draw out all our products now, we'd have our carbon backbone. We still have the halogen floating around. Oops, it's a lone pair. Still have the halide that's negative. The electrons in that carbon-hydrogen bond I'll now show as the double bond in blue, so we know where it came from. What happened to the hydrogen? Well, it lost electrons. Well, if it loses electrons, it's now going to be positive. So we should specify that positive charge. Okay, well, what happened to the green carbon? Okay, it started neutral, and we didn't really lose electrons. We could say we took 2 away, but then we put 2 back right next to it. So it doesn't really change its charge. What happened to our carbocation? Okay, our positively charged carbon. Well, that one didn't have electrons to begin with, that's why it was positive, but we now just gave it electrons. So positive plus a negative for our electrons, neutral. Okay, and so our result is the formation of that double bond and the loss of a small molecule. Okay, that loss of a small molecule, okay, we kind of kept separated, was ultimately in this case HX. So we eliminated the small molecule HX from this molecule, or from our starting material. Okay, so why would we break that bond? Okay, and we just addressed some of them. It's not a polar bond, so that's a bit of a problem. It's also not very acidic. Okay, so if I, for some reason, had a base handy, okay, so what makes a base? It has to be a proton acceptor. To accept protons, our base must have electrons. We've got electrons in our halide. We could show the halogen reacting with our hydrogen, sharing its electrons to form that HX molecule. Okay, but again, it's not an acidic bond. That's not an easy bond to break. So why do we do it? Okay, kind of a gray area in that respect. Okay, what we're doing is increasing the pi character, which ends up increasing the reactivity. We're looking at trying to stabilize the positive charge. Okay, hydrogen would rather be positive than carbon, so it makes sense for carbon to take the electrons and leave the hydrogen as positive. Okay, but we need to come up with some way to help that bond break off, because particularly in this case, that's all we've got is just our halogen. We don't really have anything to break it. Okay, well, how did we break forces in the lab? Okay, we have done this, I promise. We broke intermolecular forces in the lab in a very particular fashion. Okay, think back to one of the first labs we did, melting point. What did we do there? You added heat to the point that a solid converted into a liquid. Well, what kept it a solid? The intermolecular forces. So one of the big things that we can look for an elimination reaction is the addition of heat. Okay, and that can be written as just straight up plain heat, or that can be written as a delta symbol. Okay, symbolizing that we've added some kind of external energy to this reaction. That energy will weaken that carbon-hydrogen bond enough that we can see the pi bond forming, or that we can facilitate the pi bond forming. Okay, I know it's a bit kind of a tricky concept to deal with, but like I said, that's what we've got to work with. We know it works, we know it happens. This is the only way that, or one of the ways that explains how it happens. Okay. I know you guys loved orbitals so much, so let's go ahead and take a look at kind of an orbital reason for this. So let's take a look at step 2 again a little bit closer. In the process of this reaction, so if I draw this out, really what we've got, this is what I was talking about. I know, it's a bit messy. Then we've got our p orbital here. Okay, and that I said was our carbocation. That's what we're trying to represent down here. And what's happening in the course of this reaction is that sigma bond can freely rotate. And eventually it can rotate in such a position where a hydrogen atom on that proximal carbon, so that's this hydrogen, the electrons in that bond can end up pseudo-overlapping, okay, with our carbocation. That pseudo-overlap is ultimately facilitating the formation of our pi bond. Okay, the electrons start to notice that they can jump into a p orbital, okay, as opposed to interacting with that hydrogen instead. Okay, and because of that, we can help facilitate the elimination reaction. Okay. We've also added an extra piece of information here. B, we're going to come back to that one in a second. Okay, and by in a second, I mean right now when we move on to the second type of elimination reaction, okay, or E2 elimination, the bimolecular one. Okay, and I should have done this on the first slide, but whoops, okay, good. What we've got here is the E2 elimination. Okay, so same general idea. We're going to try and go through and do that reaction, the same overall reaction, but now when we go through and do it, we're going to do it all in one fell swoop, all at the same time. Okay, so we're going to take the electrons that were between that carbon and hydrogen, and we're going to immediately shift them over to form our pi bond, while at the same time our leaving group, or our halogen, takes the electrons away from that carbon. Okay? And in the process, what do we end up forming? We get virtually the exact same products. Okay? And I say virtually for a good reason. We'll get to that one in a second. So there's our halogen. Okay, we'll go ahead and show again the lone pair that it stole in red. Okay, with our negative charge. And I'm going to leave the hydrogen as just H for the moment. I'll show the positive. I lied. Let's go ahead and show the positive charge. Okay, and because it lost electrons, we'll go ahead and signify it with the blue. Okay, so that all happened at the exact same instant. Okay, well, we still have this issue of that carbon-hydrogen bond and why it's breaking. In the E1, we said it was questionable. We sped it up with a little bit of heat, and we said that there was the carbon, the carbocation, that the removal of that hydrogen could help stabilize. Okay, well, in this case, we don't have that carbocation. Okay, so there's nothing to help facilitate a stabilization. We could add heat, but that heat might as well break everything in our structure. It doesn't have to be the carbon-hydrogen. Okay, so in the E2 elimination, we're going to have to do something else to facilitate this carbon-hydrogen bond breaking. Okay, and that something else was kind of alluded to in that previous slide. In that previous slide we saw, okay, good, we're looking at the blue, that B symbol. Okay, and that B symbol with its electrons shared with the hydrogen. Okay, so if we went ahead and looked at our product, whoops, come on now, we would no longer have H+, but we would have BH. Okay, and in theory, at least at this stage, we would say B positive. Okay, so what is that B? Well, I'm trying to break a hydrogen bond. So my carbon structure is acting as what? What did it do in this reaction? Okay, yes, the leaving group left, but what did it do particularly with regards to that hydrogen? That's going to be our more important aspect here. Lost its hydrogen, we could use that term, or we could say it donated the hydrogen ion to that B atom. Okay, well, if it's a proton donor, then that species is a Bronsted-Lowry acid. Okay, well, if our alkane is a Bronsted-Lowry acid, then atom B, whatever it may be, must be a Bronsted-Lowry base. I wonder what that B stands for. It's a base. Okay. So we could have used the base in the E1 elimination, but that wasn't the slow part of that reaction. Again, the slow part in that reaction was forming that carbocation. Here, we need that base to break that carbon-hydrogen bond, because if the carbon-hydrogen bond doesn't break, the halogen never leaves. So one of the big dynamics with our bimolecular reaction is that our base needs to be a strong base. Okay? Anybody see any problems with that? What was the definition of a strong base? Okay, it's a proton acceptor, but what other definitions of bases are there? That's right, an electron donor. And an electron donor, we could call it a Lewis base, or we could also call it a nucleophile. Uh-oh. This is going to cause problems. Okay? When we started off this elimination discussion, we said the one thing that needed to not be present was a nucleophile. Because if we had a nucleophile, we would predict the substitution reaction. Okay? So this is where we start to run into some interesting dynamics between these reactions. Okay? We'll come back to this, we'll keep kind of hitting on it. But when we're pushing an elimination reaction, we're looking for that strong base. Okay? On the test, I will expect at least one mechanism. I won't tell you which one of these four at this point. And I will tell you which mechanism to draw out. So you'll know that whatever that negatively charged species is, I'm telling you it's acting as a base, or I'm telling you it's acting as a nucleophile, to kind of help you with the mechanism. Okay? So, let's push this a little bit harder, just like we did with our E1 elimination. We're going to look at our orbitals, just because everybody loves orbitals still, right? Can't get enough of them. And to top it off, we're going to push it into Newman projections. The way I initially drew that elimination reaction was a bit problematic. Okay, so I'll try and draw what I had initially drawn there up in our upper left-hand corner so we can get kind of a closer look at it. We had our hydrogen, we had our carbon, and then our halogen, and then I said we had the base coming in with its electrons. Okay, and I'll even stick with the same colors. Forming our double bond, and then our leaving group leaving. Okay, well, our base is coming in with what? That's right, electrons, so ultimately negative charge. What is our leaving group leaving with? Again, right? Electrons. What are the odds this base is going to come in from this face? Okay, or this hydrogen? Okay, if it comes in, it's likely going to see the leaving group, and it's going to repel away. So just like with the SN2 reaction, we have to do the E2 elimination from a backside attack. The base needs to come in as far away from the leaving group as possible. Okay? And that's not the easiest thing to see in a standard drawing, which is why we moved to the Newman projections. Okay? If we take a look at our leaving group in our first Newman projection, it can leave. When our base comes in, and I'm going to double arrow this base now, our base comes in, attacks the hydrogen. These electrons in that bond can now go form the double bond. Okay? That bond forming between our point atom in front and our carbon in back. Okay? So we get kind of a backside attack. If we look at it from the side with an orbital diagram, which is what they're trying to show, the electrons come in to form the double bond from the back side of our leaving group leaving. Okay? So you can kind of see the dynamics and the stereochemistry of that reaction. Okay? And in the process of doing that, that prevents rotation about that bond, and these R groups end up being locked in place. Okay, wherever they are. And those R groups can be anything. Carbons, hydrogens, big aromatic rings. It can be anything we want. Okay? This alignment for the E2 elimination, what Newman projection do we have here when we compare the hydrogen to the halogen? We've got the anti-alignment. Anti-alignment being our key phrase here, so when we go through and do the E2 elimination, we must have the leaving group and our hydrogen that's getting removed in an anti-alignment. You may see other phrases like they're showing here, the anti-coplanar transition state or anti-periplanar, any one of the above. Okay. Let's look at the Newman projection if the hydrogen was not in the anti-alignment. Okay, if it was in the projection that I've got drawn on the upper left-hand corner, okay, where our hydrogen is being pulled off from the same side as the halogen. So first off, we run into an issue because we're now eclipsed. That eclipsed conformation isn't a particularly stable conformation. So again, that's not a very likely conformation to begin with. Okay. If we turn and look at it from the side, the base comes in with its negative charge, sees the halogen leaving group, butt up against each other, don't like each other, repel away. We don't really see that elimination occur. Okay? I know it's a bit tricky, but what you have to realize is ultimately you need this anti-alignment when you go through and do it. So when you're looking for elimination reactions, in particular deciding your elimination products, you have to make sure that if you're running in an E2 elimination, that you have that particular alignment. The leaving group and the hydrogen must be on opposite sides of the forming double bond. Okay, and yes, we'll look at an example of that in just a little bit. In fact, that might even be the next slide. Nope, not yet. Okay, before we get into even more complexity with that, let's go through and back it down a little bit and go back to something a little bit easier to deal with. Okay, in this case, what mechanism am I trying to show? Okay, elimination for sure. How do we know it's elimination? Well, pretty sure it should stand out because it says elimination right there. So we're looking at, and it says elimination right there. So we're looking at an elimination reaction. Is it the 1 type or the 2 type elimination? Okay, we'd have to go back to our mechanisms. In the 1 type, the very first step is the formation of a carbocation. In the 2 type, it all happens at once, no carbocation. So let's take a look at the reaction I've got shown here. What do we see? First off, 2 steps. Second off, carbocation, which means, which mechanism am I trying to show? Good job. We're looking at the E1 elimination. Okay. In those previous reactions, we went through, found our carbocation, and then we looked for the atom next door. Okay, and we said, does that have a hydrogen? If it did, we took those electrons away and we formed our double bond. Okay, however, there always has to be a however, right? Is there another atom next door? Uh-oh, yeah, there is. Okay, so why didn't I take that hydrogen? Or, crap, of course now it's got to get even more complicated. Why don't I take that hydrogen? Okay, so this puts us in an interesting dilemma. There are 3 possible products here. So what we've got to go through and do is look at all 3 possible products. I know everybody's least favorite thing, but you have to draw them all out and try and decide between them if there's a difference. Because there's not a difference, and we don't need to worry about it, right? So in the case of the red one, we're taking the electrons from our hydrogen and we're forming the pi bond outside. So there's our double bond. In the case of our green product, okay, we're not touching the rest of the structure, we're just trying to keep it as simple as possible. We form our double bond there. And in the case of the blue double bond, or the blue hydrogen, what's our product look like? We form this. Okay, so 3 possible products, all from a single reactant. Whew. It's a bit dangerous, a bit heady to kind of deal with. But we need to be able to go through and decide which of these possible products is formed. Okay. So a famous guy came through and he came up with a rule here, and he said that the most stable double bond is the one that's formed. Okay. So what we're looking at here is that a hydrogen is removed from the proximal atom that has the least amount of hydrogens is the one that loses the hydrogen. So we could look at it as the poor get poorer if we're looking at hydrogens as currency. Okay, so if we say hydrogen equals money, then our poor get poorer. That really doesn't look like a word, but you know, that's why we're chemists. So, what does that mean? Well, let's go back and look at our initial structure. Our red hydrogen. How many other hydrogens are just like that red hydrogen? So we look at that carbon. Currently, how many bonds are shown? Only 2, which means there are 2 more hydrogens to satisfy the octet. If we take a look at our green one, 3 bonds are shown, which means there's 1 more hydrogen. If we look for our blue one, 4 bonds shown, no more hydrogens. So poor get poorer. Which position should lose a hydrogen? Our blue one. The answer is this last product. Okay, so if you were asked to tell me what the product of this reaction would be, you would have to give me that blue structure. The other 2 would elicit only partial credit. Okay, so now the question becomes why? Why would I pull that hydrogen off and not any of the others? Okay, well, we can always go back and evaluate stability. What's the most unstable thing about all 3 of these products? Okay, so when we're looking for stability, we're looking for charge. Okay, I don't see any charge, so then the next thing we should look for would be lone pairs. Okay, don't see lone pairs. So what's the next thing we look for? Pi bonds. Okay, and if I want to evaluate stability, ultimately what I'm trying to say is that I want the pi bond that's least likely to react. Okay, so for that pi bond to react, for any of these pi bonds to react, those electrons must come out of the structure. So why did I draw the arrow that direction and not, well, let's draw them both ways. Why did I draw the arrow that way and not that way? Okay, well, what's out here? At best, we might say there's a hydrogen out there, but that's not a lot. If we go the other direction, we run into a bunch of carbons. Okay, carbon has a lot more electrons than hydrogen. This method, not the best way to go. So we would expect our electrons in our double bond to push out where there's least amount of things in the way. When we go through and look at the next structure, okay, we've got, again, an empty spot where we can go out and react. Before we do that, we can go back to our first red double bond, and we could say it goes out that direction. So there's 2 ways that that one can react, going by hydrogens. For our green one, we really only get 1 way. And for our blue one, there really isn't any way for for our double bond to get out of that structure without going near a bunch of other electrons. Okay? So what happens is our electrons try and move out and immediately turn around and come right back because there's too much electron density in the way, pushing them back into the double bond. Okay? Well, if the double bond can't ever leave the structure, what does that mean about its reactivity? It means it's not very reactive. Okay? So we can sort of equate the stability of our double bond to its buriedness within the structure. The more buried the double bond, the more stable the double bond, okay, or the less reactive. Okay, and that's ultimately what Zaitsev's rule was looking at. All about energies, trying to find the most stable product possible. Okay? So we can put that another way, or look at it in another situation. We can look at the substitution patterns of double bonds. Okay, so we've got a sequence of double bonds here, and we've got the little equation things in the middle representing the different energies. Okay, in that first case, we would refer to it as being tetra-substituted. Okay, and I circled the 4 substituents. When we're going through and evaluating double bond substitution patterns, we're not looking at the atoms of the double bond. Okay, what we're looking at is the atoms attached to the double bond. Okay, the groups coming off of it. So in our first case, we're tetra-substituted. In the next case, we would be tri-substituted. Why do we not count the hydrogen? Because it's so small. Okay, we imply it in almost any other situation, so we're going to imply it here as well. Okay, then we can get di-substituted patterns or mono-substituted patterns. Okay, so there's a variety of different ways that you can piece this together. Okay, ultimately, what you need to be concerned with is the more substituted the double bond, the more stable it is. Okay, so come back here. In an elimination reaction, the major product of your reaction is going to be the more substituted double bond. And this is known as Zaitsev's rule. Okay. There is an exception for this. It's only for the E2 elimination, and that is if the hydrogen is sterically hindered. Sorry, if your leaving group is sterically hindered. I don't know why I did that. So it's your leaving group. So our halogen is sterically hindered, and you use a sterically hindered base. Okay. I don't want you to be too concerned about that one. I think I've got an example coming up where we'll look at that a little bit more closely. Okay. So let's go through and take a look at some examples of some elimination reactions. Okay, and in particular, this one's tricky because we're looking at the elimination of cyclohexanes. So, which mechanism do you think we're going to do our elimination in here? Yeah. Well, look to our reagents. We haven't talked about substrates yet, and we won't really directly talk about it for our eliminations, but we have talked about the base. If I'm going to use a base, which mechanism, and particularly a strong base, which mechanism am I favored to use? That's right, we're looking at an E2 elimination. Okay, so everything has to happen at once. Okay, and this is where this gets tricky. Okay, so strong base means E2, which also means we must have the anti-alignment for our double bond formation. Okay, we'll come back to that anti here in just a second. So let's take a look at our starting materials. If we say Zaitsev's rule, what would we expect for our double bond product? Okay. Well, we've got our bromine leaving group. So the bromine could go ahead and leave, but it has to get forced out by our hydrogen. So what we'll do is look to the atoms nearby. Okay. And we want to look for hydrogens at those positions. So there we go. Now we've got some hydrogens. And we'd say, okay, which of those would generate the most stable double bond? Zaitsev's rule, right? Well, if I eliminate the top one, I form the double bond between or a tertiary or a tri-substituted double bond versus if we did, I'll go ahead and mark it now in green, the green hydrogen, what would we end up getting? We'd get the di-substituted double bond. Okay, so two possible products of those two. Which one is favored? That's right, the blue one. The blue one because it's tri-substituted instead of di-substituted. So let's look at our substituents. There's 1, 2, 3 versus 1, 2. Okay, so according to Zaitsev's rule, we would predict blue to be our product. If we go through and try that same reasoning for our other one, okay, for the one down below, we'll try red and orange for this. Okay, let's put in our hydrogen, and come on, orange, work with me here. put in our hydrogen here. And we go through and do our elimination where we bring in the hydrogen down, get rid of the hydrogen or get rid of the hydrogen, and our leaving group leaves. We would end up again with possibility of two products. Okay, our red option, where we get our double bond here, or our orange option, where we get our double bond here. Okay, this is kind of neat. I didn't plan the color matching just for future reference. Okay, so we end up with the same situation. In both cases, according to Zaitsev's rule, we would predict the more substituted product. Okay, interesting. Why would I ask this question then? Seems reasonable. Probably something else is going on. Remember how I said that anti-alignment is really, really, really critical for this reaction. We must have our hydrogen and our bromine anti to each other. Okay, so that means if the bromine is wedged, our hydrogen must be dashed. So let's go back and take a closer look at what we drew in for our hydrogens on our first structure. Okay, we had blue and green, right? Okay, well, our blue hydrogen and our green hydrogen. Let's do the green hydrogen first. If it needs to be dashed, let's go ahead and say, hey, it's dashed. Let's put it in. So our green hydrogen, because we got two options there, we'll make it dashed, and we can show the other one. There's the wedged other hydrogen. How about our blue hydrogen? Okay, well, what should it be? I've already got a methyl there. That's the CH3 right here. And that's wedged, which means the hydrogen must be dashed. So when I look at this reaction, the hydrogen's dashed and the bromine's wedged. They are in the anti-alignment on opposite sides. There we go. That elimination makes sense. I should absolutely get the most substituted product. I agree. Good job. Okay, so now let's go through and take a look at our red and orange hydrogens. Okay, well, first I'm going to have to erase, clean it up a little bit. Okay, let's do the orange ones first. Remember that position has two hydrogens, so we can show the wedged hydrogen, which isn't going to be important in this case because our bromine is wedged as well. So we'll end up removing our dashed hydrogen. Or if we move to the red hydrogen, okay, now should it be wedged or dashed? Well, I again have that CH3, but this time the CH3 is dashed, which means the hydrogen must be wedged. Interesting dilemma. For the elimination to occur, the bromine and the hydrogen must be on opposite sides. In this case, I cannot physically make the most substituted product here because the hydrogen and the bromine are not anti to each other. Okay, this is where I was saying I conveniently picked orange. Okay, this ends up being the actual product when I start with this as my starting material. Okay, so depending on where your hydrogen is located, you may end up with different products. When you go through and do the elimination, make sure that you account for the leaving group, your halogen, being anti to the hydrogen. How do you know it's anti? Well, in this case, we had wedges and dashes. Other cases, what would you need to move to? Everybody's favorite. You would have to move to a Newman projection to verify that your leaving group and the hydrogen are anti to each other. Okay? It slows down your product formation a lot. Okay? If you were going to go through and draw out Newman projections, so you can remember that your bromine, your leaving group, and your hydrogen, if you're in a cyclohexane for instance, that they must be wedged and dashed. Okay? Or wedged and dashed. Okay, they have to be anti to each other for that elimination to occur. Okay, you can flip back to a few slides back where we looked at the anti-elimination for the E2 mechanism. Okay, I know it's a bit to process, it takes a little bit of practice, but I have confidence that once you draw it out a few times, you'll start to see what's happening with it. Okay. So, just like we did with our substitution reactions, we'll go through and kind of evaluate which mechanism feeds into what. Okay. When we're looking at our substrate as far as our E1 versus our E2, okay, we're getting a little bit different than we got for our SN1 and SN2. Our E1 is still focused on a stable carbocation. Okay, so that's nice. It's the same thing as our SN1. Okay, however, our E2, instead of being focused on just purely based on sterics, it's more concerned about the stability of the product. Okay, which is going to lead to, when we look at our substrate patterns, tertiary reacting faster than secondary, faster than primary, faster than zeroary. Well, zeroary is not going to react. I don't know why that's on there. That was just silly. Okay, you need at least 2 carbons to have a double bond, right? So can't possibly be zeroary. The tertiary will react faster because if we look at the tertiary substrate, so it's upper left hand corner, okay, if we have our leaving group there and we have our hydrogen here and we do our elimination, why would that form a better product than, say, a secondary or primary? Well, look at the product or the result of that. Our double bond has 2 substituents on it right away. Whereas if we went through and did the secondary or primary, secondary we'd end up with 1 substituent. Secondary we might end up with 1 or 2 substituents depending on our situation. And with primary we'd only have 1. Okay, so our tertiary substrate in the case of the E2 is going to react faster than our primary, which, believe it or not, is actually a good thing for differentiating reactions, which again we'll look at in a second. Okay. When it comes to the base, yes, this is color-coded to match or equate to our nucleophiles. It's very, very similar. Okay, I'm going to write nucleophile and then put a line through it because we're looking at the elimination right now. We want our base. For the E2 elimination, just like with the SN2, we need something that's strong. We need a strong base to push the E2 elimination along. For the E1, just like for the SN1, we don't really care about the strength of the base or nucleophile. Okay, as long as we got something there, it should be fine. Just like with our substitution reactions, you need a good leaving group. Nothing's really different there. We just talked about the substrate patterns for both the E1 and the E2. We're favoring tertiary and secondary. The E2 we can force in a primary situation, but it's fairly rare. Okay. When it comes to solvent, for the E2, thankfully we get something nice that we don't have to worry about. We don't have to worry about the solvent for an E2 elimination. Okay, so it can be pretty much anything, and it will be. For the E1, we still have that carbocation, which means we need that polar protic solvent. Okay, so it's that carbocation stability that's still pushing back onto our products. Okay, stereochemistry. When it comes to the E2 elimination, we have to be in that anti-orientation, which means we can have cis or trans products possible. And I just realized that we didn't discuss cis or trans with respect to the double bond, so on the next slide I'll talk about that. I'll have to draw it all in, but you'll get the idea. For the E1, trans is the most likely. Okay, and that just has to do, again, with stability. And we'll talk about why trans is a more stable product than the cis. Okay, but with the E2, again, because of that anti-orientation, you can get cis or trans. It depends on getting that hydrogen into that anti-conformation. The last thing is this new term regiochemistry, which is just a fancy way of saying we're going to form the most stable double bond. So it's just a question of where the double bond forms. Okay. So we expect the Zaitsev's product for both E2 and E1. We're looking for most substituted. Okay, so I'm not quite sure what color to pick there, so let's just do red. So we're looking for most substituted. Okay, tuted. That looks close enough. Okay, so I know a lot of stuff there. So let's go ahead and move to the next slide, which, like I said, I'm going to have to draw over it. Yep. So before we move into that, let me discuss our cis and trans issues with our double bonds. Okay. So when we're going to look at a cis versus trans double bond. So we saw it with cyclohexanes, and since we skipped chapter 4, we haven't really seen it with double bonds yet. So cis and trans alkenes or double bonds. Okay, so if I look at a double bond that has just two groups attached to it, two non-hydrogen groups, CH3, so we'll look at it as a butene. Or I could draw it like this. Okay, and as you guys might remember from that review slide way back, our nomenclature review slide, if we have an alkene, our suffix becomes the ENE ending. So when we go through and evaluate these two structures, we've got 4 carbons in each. So we're looking at a but. Because of the double bond, it's an ene. The ene is a new functional group, so I need to specify where that double bond occurs. And we'll put it where we give it the lowest number. In this case, it doesn't really matter. We're going to get the same number. 2-butene. Okay. Unfortunately, if we go through and evaluate these two structures, though, they are not identical because there's no way I can superimpose them. But just like with a single bond, okay, you might think, oh, well, why can't I rotate about that bond? You remember way back when we talked about orbitals? It said you can't rotate around a pi bond because then you break the p orbital overlap. Without that p orbital overlap, you don't have the double bond anymore. Okay, which means I cannot rotate about the double bond. Okay, so that means these two structures are different. If they're different, if they're isomers, I have to be able to name them something different, and that's where we get the cis and trans nomenclature from. Okay, so as you might be able to guess from what we learned with the cycloalkanes, if our major groups are on the same side of the double bond, we'll refer to it as cis. If they're on opposite sides of the double bond, we'll refer to it as trans. Okay? Now trying to decide between these two, which was what I addressed just a second ago, which of these is more stable than the other? Okay? Well, to do that, we would kind of have to think about the electron clouds. Okay? So this CH3 has a lot of electrons, this CH3 has a lot of electrons. Same kind of deal over here. Electrons want to get as far away from each other as possible, which means which conformation is more stable? The trans. Okay? Just because those groups have more space. So when you go through and do an E1 elimination, we don't form the double bond right away. We've got that carbocation connected with a sigma bond. So that sigma bond can freely rotate until we lock in the position where our hydrogen is, and then we can do our elimination. Okay? Which is why when we do the elimination, or an E1 elimination, we almost always see the trans product form, where we get our largest groups as far away from each other as possible. Okay? let's see where we are. Well, never mind. I remember where we are. So, kind of the be-all, end-all of all of this is, now that you know each of these individual mechanisms, you now need to be able to decide, given reagents, given starting materials, you need to be able to tell me what the product is or are of that individual reaction. So you have to be able to evaluate what substrate you have, what reagent, nucleophile or base, what leaving group, what solvent, and try and put that all together to try and decide what type of mechanism occurs. Once you know the mechanism, you can then try and predict the product. Okay? I know it's a lot to put together and it requires a little bit of practice. Practice you're not going to have a lot of time for, so I think I'm going to cut back what's on your next exam. Okay, so we won't look at Chapter 8 at all. So, what things to evaluate? Number one, I would look for the strength of the nucleophile or base, because that's going to determine which order of your reaction, be it a 1-type order or a 2-type order. Okay? A strong nucleophile or base pushes the 2-type reaction. Okay? So if you see a negatively charged reagent, you're thinking immediately SN2 or E2, right off the bat. If you see your nucleophile with a hydrogen attached to it, you're pushing the E1 or the SN1 reaction. Okay? Technically, if you see a hydrogen attached to your nucleophile, you're doing both the SN1 and the E1. Because if you remember, I don't think we've talked about that complication yet, but if you have the 1-type reactions, they compete directly with each other. Okay? So, deciding between 2 negatively charged nucleophiles, whether you get a elimination versus a substitution, hinges on whether or not you have a base or you have a nucleophile. Okay? The more bulky your base, the more likely you'll see an elimination. Okay? So the classic example of a bulky base, this is for sure on a later slide, but let's go ahead and put it up here anyway, would be T-butoxide or tert-butyl. So if we do tert-butyl, there's 1, 2, 3, 4 carbons with an oxide. We have T-butoxide. Okay? These carbons add enough electron bulk that it prevents this negative charge from acting as a nucleophile. Okay? Remember, to act as a nucleophile, it has to be able to get in and react with carbon atoms or things not hydrogen. Okay? Those atoms tend to be buried within structures. If your nucleophilic species, or what you think is a nucleophile, is really big and bulky, it's not going to be able to get in to react as a nucleophile. It instead is going to try and find something more positive that's a lot easier to access. For instance, a hydrogen. So it would act primarily as a base. Okay? There are a few other names that show up later, but you don't need to worry about those names. T-butoxide or this structure are going to be your big red flags for an elimination reaction, in particular the E2 elimination. The next part is evaluating substrate structure. Okay? Our primary halides are going to undergo SN2. Okay? You could see the possibility for an E1 elimination, but it's really, really rare. Okay? How would you know? You see a primary halide, how would you expect it to go an E1, not the SN2? Well, what did we just say in the previous step? Okay, an E2 needs a bulky base. So if you had a primary halide and you had the tert-butoxide, you might see the E2 elimination. Okay. Otherwise, primary halide, you assume the SN2 reaction, you're doing a substitution. Okay. If you have a secondary halide, okay, this one's a bit of a raw deal to get. Okay. says to look to Rule 1 for help. Why? Because if you have a secondary halide, all mechanisms are possible. You get the SN1, E1, SN2, and E2. Okay, so you need to find something else to try and push you to one mechanism versus another. If you don't find anything else, you have to assume all four are possibilities and run the reaction to see maybe you only get one product out of that or two products out of that. Okay. If you get a tertiary halide or a tertiary substrate, you're going to end up with a mixture of three possible mechanisms. You get the SN1 and E1 or the E2. You absolutely will not get the SN2. Why not? The SN2 was all about steric hindrance. That was its primary, if not only, concern. The tertiary halide is so sterically blocked that you cannot get the SN2 reaction to occur. Okay. Another big red flag for elimination, particularly the E1 elimination, and this is how I'll ask questions and kind of grade, is high temperatures. Okay, so if you see heat or a delta symbol involved with the reaction at any point, you should be thinking elimination. Okay, and in those cases, you should probably be thinking the E1 elimination, but you should check for that bulky base just in case. Okay. So, kind of summarizing everything together, this is the generic setup so you can see everything kind of in front of you. Shows the rates and all of that kind of fun stuff, and I just talked about this. So the idea is trying to sort through it and be familiar with what's happening at each stage of the game. Complications. So that last slide was ultimately how everything normally works. Everything runs smoothly. You're just told that that's what you're doing. These are the orders you move through. Okay. Once you've decided that that's the mechanism you're going to do, you now have to be aware of the complications of each of those mechanisms. Okay? For instance, in the SN1 reaction, you lose stereochemistry. So if you started with a stereocenter, your product must be racemic. You end up with two products. Okay? To make matters even more complicated with the SN1, if an E1 elimination is a possibility, then you end up with three products. You get the two products, the enantiomeric products from the SN1, and then you get the extra elimination product as well. Okay, so SN1 reactions are a bit of a pain because you get, for that matter, E1 reactions are a bit of a pain because you end up with three possible products. Okay, with the SN2, our primary concern with that one is that you get inversion of stereochemistry. If you start R, you go to S. If you start S, you go to R. Okay? Thankfully, that's fairly minimal as far as the SN2 goes. With the E1 eliminations, it's not really a complication, it's more just kind of a summary. You're looking at trans alkenes. You want your SIS products, so your most substituted double bonds, and you're going to expect that to run simultaneous with the SN1 reaction. Okay? With the E2 elimination, the E2 is just going to be kind of a pain. You have to be aware that you've got the anti-alignment, which means you're going to have to use Newman projections. Okay? This means that you get cis products as a possibility, even though trans are more favored generally. You still expect to see SIS products, again, the most substituted double bond. If you move into more advanced organic chemistry, you might hear Hoffman products. I'm not going to ask anything about Hoffman. Okay. More summary stuff. Okay, this is an attempt to summarize all of the big things as far as your nucleophiles, bases, and leaving groups. We've got the three primary rules with your nucleophiles. You must have donatable electrons. It must be negative, or a strong one will be negatively charged, and typically the lower electronegativity, the more nucleophilic. Okay, so those are your primary rules for nucleophiles, and for that matter, for bases. Okay, really the only difference between a nucleophile and a base comes in with the base definition, which I've got numbered as Rule 5 for some odd reason. The more steric hindrance, or the bigger your base is, the stronger the base. Okay, ultimately that just means the less nucleophilic. Okay, and there's the example T-butoxide that we talked about already. Okay, when it comes to leaving group, it's ultimately the inverse of the nucleophile. We're looking at something that can stabilize or minimize the electrons that it's taking, so that lone pair. Okay, they are typically extremely weak bases, which is why they showed, or why these reactions showed up with alkyl halides, because halides are terrible bases. Okay, that would push us into Chapter 8, so I'm going to go ahead and call it quits, and we won't talk about Chapter 8 chemistry at all, because I'm fully aware that you guys have enough other stuff to deal with this. Trying to think if I can tell you anything about exam design. Let's go ahead and attempt to write some stuff out here. Exam 2. So things that we're going to have to cover here. You will guaranteed see some questions on chairs. I would estimate probably 2 questions. Okay, one probably multiple choice, one probably a short answer kind of explanation. So that's what, Chapter 3. You then see all sorts of questions on stereochemistry. Okay, I gave you that long quiz for a reason, to get you enough practice with that so that you can hopefully do really well with stereochemistry. And that's going to be Chapter 6. Okay, the last thing we've got is our alkyl halides, which will be Chapter 7. From that we get some nomenclature with our halogens. So nomenclature, I guess we can just call it nomenclature halogens. And then what else do we get? We've got your substitution reactions, and you've got your elimination reactions. Okay, so that's a lot of material, or a lot of new material. Arguably, I would probably push this as probably your hardest test in this class. The other tests are ultimately repeats of this material, so it keeps building on this material. So if you don't practice this, the other exams do appear harder, but it's ultimately all coming back to this material. Okay. One of the things that I'm going to add here to kind of help facilitate with this test, a little bit nervous about mentioning it now because I'm afraid it's going to turn into people not studying for this. Okay, you really, really need to study and practice this material. It will take time. It's going to be hard. You need to do the practice for it, even without the 8.5 by 11 sheet of paper that I will let you bring in. Okay, so you're allowed to bring in an 8.5 by 11 piece of paper full of notes. Okay, on one side. These notes must be handwritten unless you have expressly gotten permission from me. Okay. Ultimately, what I want to avoid is people photocopying or just copying slides, because that's not going to help you. The idea is that if you handwrite it, hopefully you'll remember it at least a little bit better. Okay, if you do the photocopy method, I'm not going to allow you to keep those notes, and I'll deduct points from your exam. Okay, unless, like I said, you ask specifically for my permission, and then I would need to see those notes well in advance of the exam. Okay. I'm going to get a quiz posted hopefully by Saturday or Sunday with more questions on substitution. questions on elimination, and then questions with a mix of everything. Okay. Sorry I wasn't there on Wednesday to be able to collect the quizzes so that I could get them graded and back to you for feedback. If you've got questions about the quizzes, please feel free to send me an email, and I will try and help you as best as I can. Okay? So good luck studying this weekend. If you've got questions, please shoot me an email, and I will try and respond as fast as possible. See you on Monday.